One of the tools we're going to use to calculate the probability of certain outcomes along a normal distribution is that of the z-score. But before we turn to that, I just want to talk more broadly about the z-score in general and what it's accomplishing and why it does the things it does. So the z-score is really about comparing various points along a distribution, along a normal distribution, comparing how far that value is to the mean in terms of standard deviations. Okay, and so what I have here are two distributions. They are this is roughly the distribution for male and female adults in the U.S. Okay, so for males, the average is about 70 with a standard deviation of 4, and for females, it's 65 and a standard deviation of 3.5. So what a z-score helps us do is put into context various points along a distribution. And what I've highlighted here is I have consider a 6-foot male and a 6-foot female. Now, growing up in I guess any society, you have a sense as to how rare or how rare a 6-foot person is of male or female. But we can put that into context of the distribution if we think about the standard deviation. So this is more flexible than just obviously this scenario. So for a male distribution here, we have what do we know? This is a person that is 2 inches taller than the mean. Okay, and that's one way to express it. They're 2 inches taller than the mean, and similarly for a female, that would be 7 inches taller than the mean. Right, so we could calculate just x minus mu. Right, this is a deviation from the mean, which we've been discussing for quite some time now. So 72 minus 70. Let me write a little bit better here. So 72 minus 70. So there's a deviation of 2. Likewise, with the green situation, we have 72 minus 65, or a deviation of 7. Okay, so that's helping to put it into context. And in this case, that's not that that's pretty good. We know that's a 7 inches taller than average and a 2 inches taller than average. But what the z-score does is brings that one step further and compares it to the standard deviation. Now, in this scenario, it's probably not that important to compare it to the mean or to the standard deviation. But we'll talk about it in another example here in a moment why this extra step is so helpful. So the last step here is we simply do x minus mu and compare it to the standard deviation. And this is the z-score. Okay, so we say 72 minus 70, but then we put it into context of how spread out the data tends to be. And here we get 1/2. So we are 1/2 standard deviation above the mean. We can finish that out over here. And while we know, of course, this 72-inch or the 6-foot female is further deviated from the mean, let's put it into context of the standard deviations. So the females have a little tighter of a distribution, and so this becomes 2. So we are a full 2 standard deviations above the mean. And that's going to help us put into context how rare of an occurrence that is. And in fact, we'll use this type of methodology to calculate the percent likelihood that we would find a random person that tall. And that would vary depending on if we're talking about males or females, right? It'd be more likely to find a 6-foot male and less likely to find a 6-foot female. And that would be, that's directly related to the fact that this is, for males, it's only 1/2 a standard deviation above, and for females, it's 2 standard deviations above. Now, I said we'd talk a little bit more about why that standard deviation is so important, and I just want to, outline. Perhaps we could find a population where the distribution was very tight. So maybe I don't know what this would be. This would be swimmers that also have I'm just going to make this up on the fly, they have a mean height of 67 inches. I don't know if that would be any way true. I feel like they might be taller than that, but we'll go with that. So let's say this group has a mean of 67 and a standard deviation of, say, 1.5. Okay, maybe these are synchronized swimmers, so they're all very much the same. And so if we then wanted to think about a person at 72, then the situation changes a little bit. So we wouldn't want to just say, well, this is 72 minus 67, so 5 inches above the mean. Because in some sense, this would give the impression that this is, less extreme than the female scenario. When we put that into context of the z-score, bringing into play the standard deviation, try to fit it in there, we get, what is this, 5 divided by 1.5. So we get, what is that, 3? I ran out of space, but that's, the z-score here is 3.33, right? I think that's, yeah. So we now know that person at 72 inches is a full 3 1/3 standard deviations above the mean. And that's what's telling us that it's more extreme, not just the deviation. So again, the deviation here is only 5, but the deviation related to, or in terms of standard deviation, is more extreme. That's over 3 standard deviations away from the mean, telling us that to find somebody that is 72 inches in this, what did I say, synchronized swimming population of a mean of 67 inches, that's more extreme than if we just simply found a 6-foot female, in adult in the U.S. So bringing it into context of the standard deviation is important. And again, what we're touching on here is how rare those events are. One last thing to talk about the z-score is that these can be negative. So notice with deviations here, we're not squaring these deviations like we have been when we were building the standard deviation. This is, there is no squaring here. So if we're talking about a value of, anything less than the mean, it's going to come up as negative. And that's going to be important to remember as well, is not to drop that negative value when we move forward. So that's a little context as to the z-score, where it comes from, or what it, why we want to put these things into the context of the mean and the standard deviation, right? We want to be able to describe not just the height of this person, they're all 72 inches, but put it into context of the mean and the standard deviation.